Okay, so lesson 6 is going to be called Put Call Parity and the Greeks. This will be a pretty quick lesson. I just want to introduce a couple of concepts that I'll use then in the next 4 lessons. So I'll start off by naming V to be the value of a portfolio of derivative securities, all based on one underlying asset. So this could be, more than one option based on the same underlying asset. Really, for what we're going to be doing this week, it's going to be just a single thing, either one call option or one put option. And then the rates of change of the value V with respect to the pricing parameters, so that would be the asset price S, the volatility sigma. These are going to be things that are useful for hedging. And these rates of change are called the Greeks of the portfolio. And they're basically just the different derivatives you can take of the Black-Scholes pricing formula. So we're going to consider a portfolio containing a single European call option. And basically the way this week's going to work, if you've looked at the homework already, I'm going to go through the examples of how to compute the Greeks using a call option. It'll be very similar, but just a little different to do it for a put option. And so the homework is going to be a put option, but you should be able to refer to the calculations for the call option and up to just a few things being reordered and some different signs. It'll be very similar. And then there's also, well, I'll get to this in a second. First, I'm just going to remind you about the Black-Scholes formula. So the inputs to the Black-Scholes formula were the asset price S. And so this is going to quite often in these slides also have a T associated with it. And that just means the price at a certain time T. If there's no T, we kind of mean the price right now. And sigma is going to be the volatility. K is the strike price, so this is the exercise price of the option. Little r is a continuously compounded risk-free interest rate. Capital T is the maturity date. Q is the asset dividend rate, and this is a continuously compounded rate as well. And then little t is going to be time. So you could think of that as the current time. And really the way capital T and little t are going to show up in the pricing formula is capital T minus little t. And so that means some date in the future minus today. And so that quantity, capital T minus little t, you can think of that as the time left until the maturity of the contract. So the Black-Scholes formula for a European call option. So I'm using the same notation that is used in the textbook, and so this is for some reason treated as a function just of 2 variables, S and T. But it's really has several more, has all of the variables that I had on the previous slide in it. So you have the dividend rate, you have maturity, current time, strike price, and risk-free interest rate. And then we also have this function, capital phi, and that's just defined as the integral from minus infinity up to z of e to the minus x squared over 2 dx, and then normalized by this factor of 1 over the square root of 2 pi. We have a function d plus, which is also a function of all of the arguments of the pricing formula. And essentially, it's not necessary to write d plus as a separate function and put it in here. I could actually just write the whole thing out, but again, it just gets kind of unwieldy to do that. And now that we have tools like the product rule and the chain rule, it's actually more convenient to treat functions of functions separately like this. So we had a d plus in the first term of the pricing formula. We have a d minus in the second term of the pricing formula. And these 2 functions are very similar. And where they differ is just that d plus has a plus sigma. Oops. Okay, I can't highlight that, but it has a plus sigma squared over 2 in this part here. And d minus is actually equal to d plus minus sigma times the square root of capital T minus little t. And all that changes is that this plus sign here becomes a minus sign in d minus. So the plus and minus subscript on the d here just refers to whether this should be a plus operation or a minus operation. Okay. Then there's a relationship between the price of a put option and the price of a call option. So if I let C of t be the price of a European call option and P of t be the price of a European put option on the same asset with the same maturity date and the same strike price, then the following relation holds. And this is called put-call parity. And it just says that the price of the put option plus S times e to the minus qt minus t. So it's basically, this is just what the asset's going to be worth. If it's paying some dividends, it's going to be a little bit more. Then minus the value of the call option has to be equal to the discounted value of the strike price. And so what we're really trying to do here is relate the put price and the call price. And so in the homework, I've asked you to do two things. So I'm going to show you how to calculate the derivatives of the call price. And then I'm going to ask you to calculate the derivatives of the put price. And so I want you to actually, in the homework, compute those by taking derivatives of the formula. But you can check that you got the right answer by taking derivatives of this put-call parity relationship and then just plugging in. So if I took the derivative of this, for instance, with respect to S, this term would just be dc ds. That's going to be something that I show you how to calculate today. And so you'll end up with an expression for the derivative of the put price with respect to S, these two other terms, and something that we already know. And so that'll give you an easy way to verify that you've got the correct answer. Then the Greeks are, and they're just the different derivatives of the pricing formula, but they all have names that are Greek letters. So that's why they're called the Greeks. It has nothing actually to do with the country of Greece. So the rate of change of C, so it's the rate of change in general of the value of the portfolio. But since for today's lecture I'm considering my portfolio just to be a single call option, I'm going to just say C is the value of my portfolio. So the rate of change of C with respect to S is called delta, and that's just going to be the partial derivative of C with respect to S. Second one is called gamma, which is the rate of change of delta with respect to S. And since, so partial derivative of delta again with respect to S. And since delta was the partial derivative of C with respect to S, gamma can also be the second partial derivative of C with respect to S squared. Then we have theta, which is the rate of change of C with respect to T. And so that'll just be the partial derivative of C with respect to T. Rho, which is the rate of change of C with respect to the risk-free interest rate R. So it's the partial derivative of C with respect to R. And then vega, which I'm not sure this is actually a real Greek letter, but it sounds kind of Greek, so I guess they threw it in with the group, which is the rate of change of C with respect to sigma. So partial of C with respect to sigma.